Good afternoon, everybody.
Good afternoon.
Yeah. So it's good to see you all here at Build. I'm Mark Russinovich.
And I am Ion Stoica.
And we've got a kind of a fireside chat today, but it's a fireside chat where we don't have a moderator. We're moderating ourselves. So we're going to be talking through a bunch of questions related to AI infrastructure, models, architectures for AI. And it should be a pretty engaging conversation.
Hope so.
Yeah. So I think we can start by talking about a little bit of our background and why we're up here talking about these subjects. So Ion, you've got a background where you've had some amazing impact on the industry in data analytics and AI, in your role as a professor, in your role as a startup founder, Ray, VLLM, Databricks, Spark. Why don't you tell us a little bit about your background?
Yeah, so actually, starting around 15 years ago, at Berkeley, we started to develop a little bit more, quite a bit of systems, a few systems, initially in the space of domain of big data. And started initially with Mesos and Spark. Then after that, Ray, and more recently, VLLM, AGLang. And I think at a high level, we always looking about, obviously, trying to understand and to figure out what is a problem you try to solve. And also a little bit careful about the trends. What I mean by that, a problem you have today, is that problem going to be bigger tomorrow than today? And, like things like, obviously, Spark was scaling up data analytics and making more interactive and much better support iterative kind of patterns like machine learning. Then Ray, scaling complex AI workloads like reinforcement learning on heterogeneous hardware back then. And of course, VLLM, it was clear that trying to exploit the parallelism inherent of the GPUs, but then the memory it was a bottleneck. So trying to alleviate that bottleneck and things like that. There's the one thing I want to say, because we are at the Microsoft conference here, is that I'm very happy that actually some of the things we've done has impact also with our kind of collaboration and partnerships. As you know, Spark and kind of Databricks, great, fantastic partnerships with Azure Databricks. And actually today, we also announced a partnership between Azure and Anyscale is around Ray. So
yes,
very happy about that, and very much looking forward to this partnership to grow.
Likewise, yeah, it's been an awesome partnership.
Yeah. So, on my side, you Mark, you had so much contributions. You shipped sysinternals. Then
have you ever used sysinternals, Ion? I didn't put him on the spot.
So, but
how many people have used it?
But you architected Azure, Azure infrastructures, which I did use. Yeah. and then you are now building and architecting AI infrastructure for Azure, and security you are leading. So one question I have, you've seen all these kind of phases, and you've been in distributed systems for a long time and security. So what is new, and what is old? What you still applies, and why is no longer applying?
Yeah, well, that's a good question. I think one of the things that still holds, and this holds, I think, you'll even say for infrastructure and systems, is the fundamentals are still in place. I think if you take a look at fundamentally what's changed, it's these non-deterministic systems that are now carrying out workflows that they create on the fly. And that introduces a bunch of new risk area. In some sense, humans are non-deterministic agents creating workflows on the fly. But humans, you can hold accountable. Also, humans, I think, in general, are more reliable than the AI systems we have today. And certainly, when it comes to humans, we designed our systems around human speed and scale. And when you have agents now that are intelligent running around, they can perform lots of damage in a very short period of time. So I think if we get into it a little bit later, we'll talk about some of the things like prompt injection, risks around that, risks around jailbreaking, risks around hallucination. All of those things can cause workflows to go awry and for the system not to behave as you intend.
Yeah, and what about, this kind of, and you mentioned about the fundamentals still remain, but again, to be, more precise about concepts like consensus, consistency, kind of distributed scheduling, which of these concepts are kind of remain more or less the same, which one are changing, are morphing in support to support new workloads?
Yeah.
Yeah.
Well, I think, we talk about AI and running these agent workloads, and you talk about the LLMs and hosting the LLMs. The things like the consensus around the infrastructure, knowing what is available and online. Things like load balancing still matters. Locality matters still. So you want to route requests, especially when you talk about KV caches,
yes.
which is the context. You need to make sure that the requests are going back to the same systems. Otherwise, you're going to be wasting compute and bandwidth as you're moving things around. So all of those things still apply. I think, and this is an interesting question, I think, for you, is are these systems stateless? Do you consider them stateless or stateful?
I think it very much depends. Certainly, because I witness a serverless trend. I think that quite a few systems becomes more stateful. There is because just the overhead of bringing the state in and saving the state if needed for the next operation in some cases is too high. And it's not only the state, reading the state and saving the state, it's initializing, right? If you are talking about initializing the GPUs and so forth, can take a long time. So this forces you to be more stateful. The problem with that is that it complicates, like we all know, the fault tolerance.
Yeah. So when it comes to these distributed infrastructures for AI, which include the GPUs, high bandwidth interconnections, the KV cache, when you look at distributed systems through its evolution, what assumptions change with an architecture to support this kind of computation?
Yes. So I think it very much, great question, very much depends on where you are coming from. So you're coming from, Spark, is like big data. It's like, MapReduce++. It's a bulk synchronous processing, which is model, which is a pretty simple model, right? You partition the data, you have stages. At every stage, you have apply the same task on different partitions and do a shuffle between them. What happens with, for instance, you talk about KV cache and inference, things are becoming so much more coupled, tightly coupled. If you think about mixture of experts, and then you have the KV cache and you need to distribute it across different GPUs on the same node and even across nodes, then things are becoming, everything becoming much more coupled and more difficult because of that. Now, if you come from maybe HPC, maybe you can say, I told you so.
Yeah.
But even there, I think that with HPC, it was much more, you don't have such a tightly coupling between the data and kind of, and the compute, because even there, the data was, you don't have actually in traditional HPC, you don't have a lot of data to start with because you do simulations, right? And things like that, right? Yeah. This was kind of the workload. So I think that's kind of what it is.
Yeah.
And this creates a lot of challenges. And things even you're talking about load balancing, things are changing so much more quickly. If you think about, expert parallelism load balancing, because it can change from layer to layer when you go in the forward pass to do the inference to do serving. And the other thing what happens, I'll probably talk more about that, is that things evolving so quickly, right? by the time you build something, you have new requirements. It's never ending.
Yeah.
Yeah. So, we have this kind of, I remember, like it was 10, 15 years ago when people started, the cloud computing and so forth, and people are saying, the data center is a new computer. I'm just curious, right now, is that kind of abstraction still of actuality? Because now you can have training, spanning different availability zones and things like that. I'm curious about that.
Yeah, well, I mean, I think if you take a look when that statement was made, it was when a data center was, hold all the compute that you could imagine in the data centers at that time. Even if you take a look at the evolution of Azure as a hyperscaler, the availability zone kind of became a unit of compute. But even in the availability zone, we have multiple data centers typically. It's not just one data center per an availability zone. And then you have a region, you have multiple availability zones. So even for traditional IT workloads or serverless computing, your application can be spread across many data centers. Now, you mentioned distributed training and AI training, and that's where you run into these, the AI super factories, as we call them, where you've got massive data centers just filled with GPUs specifically to host that training workload. And for that, we passed the line several years ago of a single data center being enough to hold the scale of the AI supercomputers that we're building now to train these frontier models. And then, over the last couple years, we've crossed a line of even one region of data centers is not big enough to train these models. And now we have these Fairwater systems like that we've launched, these AI superfactories, where there are multiple Fairwaters in Wisconsin, multiple in Atlanta, and they're connected with a dedicated network so that you can have a job that spans the GPUs across both regions with a very direct cable between them, doing RDMA across the two regions.
Yeah, it's fascinating. Now, going back again, we discussed a little bit about serverless.
Yeah.
Right, the serverless
my favorite
services.
subject.
Yeah. So what does it mean in this kind of when you have today's long-lived agents, right, which can go hours, sometimes days.
Well, if you talk about serverless, it's kind of people speak about it synonymously with containers. Serverless equals containers.
Yep.
And when people think containers, they think the original serverless containers, which were like Lambda or Azure Functions, which are short-lived, and people conflate serverless with short-lived applications or pieces of code. When in fact, serverless doesn't have an opinion about what code runs in these containers, and so you could put SQL Server inside of a container, and it can run for years. And it also can be monstrous. It can have terabytes of memory. So I think, for me, I separate the two. And I say serverless is, you don't worry about the infrastructure. It is containerized for the most part, although we talk about lightweight containers now, and WASM sandboxes, which are also a form of serverless. But that's where I think the whole trend, if you take a look at Azure's architectural evolution, we're moving everything to serverless. We're moving the whole infrastructure to containers that are on a serverless infrastructure that is doing the scheduling and placement and for the job, which is expressing constraints.
So now, continuing on that note, we have, we build these infrastructures mostly to serve requests initiated by people directly or via BI tools and things like that. But now we are moving rapidly to an age of agents, to having agent loops instead of just request as a unit of work. How does this impact do you think about architecture stack?
Well, I think we're still at the early days of this, actually, because just in the last few years, we went from chat to now agentic systems, which are this loop where the agents are talking to other systems as part of their computation. And they might even be talking to other agents. And so when it comes to how you define an agentic application that consists of these things, I think we're still in the early days of specifying the application model for these and a lot of it is, I think, still ad hoc, but we're getting towards, what is an agentic application? What are the components? How do you place them for efficiency? How do you automatically deploy them instead of taking piecemeal and deploying and connecting them together after the fact? So in my opinion, I think that we're still early to that, but I'd be curious to hear about what you think.
I think we are early. The one thing I see is that constant increase in complexity.
That's for sure.
Even the definition of agents. What was an agent? Well, it was an agent, an LLM invoking a tool. But now it's much more than that. You have a tool, you have an entire harnessing, right? Which can be very complex, right? So now, and then you are talking about some kind of continual learning. People talk more and more whether this happens in context, continuously evolving the prompt, and in some cases even updating the weights, right? So kind of like RL. So, and then you have this kind of, you need something to support very diverse and complex, application. You need to do, for sure, kind of the inference. Then basically arbitrary application, running arbitrary application, because that's part of the harnessing, right? Yeah. And then maybe you are going also to do some kind of training if you want to update the policy. And so that's kind of things. And when you have the models, like of course you can have the models which is going to be collocated. It has to be collocated because if you want to update it, or it just can be, something running outside. It can be, like OpenAI or like the new models released by Microsoft. So that's kind of, it's so complex. So you need to think, to have something which is very flexible to support these workloads. And yeah, I think that we'll see. I assume that in time, things will stabilize one way or another, but we are very early.
Yeah. So
like you said.
One of the things that I'd be really curious to hear your thoughts on, in the systems that we've designed, they've largely been deterministic. You design the system, you've got a workload, you optimize for it. These systems are inherently non-deterministic, as we talked about.
Yep.
And so how does that change the way you design a system?
That's a great question. And just to be clear, one of the reasons they are non-deterministic because obviously the LLMs themselves are non-deterministic. If you send the same prompt over and over again, you shouldn't expect, or you are not going to expect the same results. Actually, in some cases, you rely on that to get diversity in order to get a better solutions. So I think, it's like there are a few things to consider. One, first of all, what is your output? And in some cases, like with coding and so forth, the artifact can be still deterministic, right? You use this to optimize the system, to synthesize even a system. And that one kind of is deterministic. You can have harnessing tests and so forth to check, and then you can have metrics to hill climb. If you want to optimize for throughput, for latency. So the output is still kind of deterministic. I think now this doesn't answer the question about how you debug your kind of evolution systems or agentic system. And unfortunately, it's like you have to presumably, and what you do is record the inputs and outputs and the traces, and then try to replace the traces, right? To find what the problem is, if there is a problem.
Yeah. So when you talk about an AI stack, you talk about GPUs, network, you talk about different types of accelerators. Where do you see the optimizations happening, the most important ones? Or, or have we reached some limit someplace where there's the bottleneck that we need to focus on?
I think clearly will happen. I think there are three levels or optimizations will happen. At the top level, there will be many algorithmic optimizations still. So I assume that a few order of magnitude improvement over the next few years will come from the algorithms, What I mean by algorithms, if you look like, for instance, just inference or training. Right now, of course, the workload changes, you have agents, you have much larger prompts or, of course, outputs. The context, again, is much larger. You see a lot of optimizations and architectural optimizations, software architecture, like, for instance, sparse attention, different kinds of attention. You see different layers, different attentions. And now you see even within the same layer, different attentions. Even maybe you'll have per token, learned attentions and things like that. So that kind of can give you a big improvement. Of course, this comes with a lot of complexity. Then, obviously, you are going to have the GPUs, the accelerators, which are going to still make progress, 1.5 or 1.6 every year, improvements. And that's coming, again, with complexity, because it's not like Moore's law used to be, right? The instruction set architecture is more or less the same. How you get these improvements, a lot of them is by adding new instructions which are targeting particularly new segments of the workloads. Right? I expect you are going to have more and more instructions in the GPUs to target this kind of sophisticated attentions. And then from the inherent, this will go slow, a little bit slower. You are still going to have smaller transistors. You are going to still be more power efficient. The power per flops will improve and things like that. But these are multiplicative, right? So when you multiply them, you can get massive gains in the next few years.
Okay, I have another question for you. Because you've been involved so much with open source in AI infrastructure and analytics, do you see a canonical open source based stack? And do you think will converge, or there'll be diversity?
I think that there is some stack which is used by companies. There is, it's like, and, you see, you have at the lower level Kubernetes or Slurm. Under the hood, if you want to move, because everyone now has to want to have a freedom to move across regions or from region to region, maybe you have something like SkyPilot. On top of that, you have to have some framework like Ray or Pathways or something like that, which helps you to distribute this kind of AI workloads. Then obviously you have PyTorch and so forth. So I think you can put together this kind of stack, and then you have VLLM or HGLang or whatever, TensorRT LLM as the inference layer. And then post-training, you have kind of VERL or SkyRL and things like that, right? So you can create a stack, and you have a stack. I think a pretty good stack. The question is about, what will happen and how this kind of stack will evolve. Because it's like, the one thing which I see in terms of the complexity increasing is that we used to build, one of the things, when you teach students, right, and we learn ourselves, that how do you build a complex system? You build this kind of in a modular way, right? So you have these components with nice abstraction, clean abstractions, which abstracts away the implementation, right? So then you can evolve and each of them independently. Now, the problem is that, and this is when we are talking about these layers and all these components, the problem is that as we know, it also comes with some overhead. And it used to be perfectly fine to say, okay, we are going to spend a few percent, 10% overhead to have this kind of nice evolvable system, because at the end of the day, we can be even faster because we are going to evolve these systems, and the system is going to evolve quicker. But now, it's so much breaking the layering, and it's called cross-layer optimizations, right? It's like, this is what I see, everything, right? So, I don't know, it's like, in some sense, it's like all these layers are going to get crossed and broken. And I'll see you can do maybe in an orderly way, but I don't know where you are stopping. Is this collaboration between Ray and Kubernetes with you guys? And but what is the thing here is that something like Kubernetes wants to know more information about the applications from Ray to make more intelligent decisions. Something like Ray, which is up there, they want to know to have more control to tell Kubernetes what to do. Right? So you can enlarge that. But I don't know when you stop, because of course you are no longer going to have this kind of narrow abstractions. Yeah. I think that's very interesting.
So we've got about 5 minutes left, I think.
Yeah. So one question I do have for you, it's. How do you think about, we are talking about the workflows, agents, and so forth. Is that, you think about like a boundary to two different kind of patterns of workloads, or you think are...
For agents and
workflows,
and workflows.
Traditionally what you call it.
The beauty of agents is that they can make workflows dynamically. And I think that this is, instead of you having to go and prescribe a workflow and write it out, you can give AI a problem, and it'll go figure out how to execute that task and come up with a workflow dynamically. When I look at those systems, if you've got anything where the workflow is going to be repeated many times, you want to make that deterministic and not rely on an AI to make it up every time you got the problem. So I think where things are not well defined, where they're very ad hoc, then AI and agents are great for making up the workflows and solving the problem. But for anything where you've got a repetitive process, you should go try to make it deterministic, because it's going to be much more efficient, much more reliable, and much cheaper. So all of those things are going to be true. And I think that this is where I see people over-rotate on, I can have an agent go do this thing. When I look at it and go, actually, you could just write a simple workflow.
You can have the agent synthesize a workflow.
That's right. That's right. Yeah, that's the other way to do it, is have the agents make the workflow, and then the workflow is deterministic.
Yep. Yeah. That's what I mentioned about, so the other thing is that we used to have, you have training and you have serving, separate deployments and things like that. But now with this kind of, post-training, starting even earlier on from reinforcement learning with human feedback, and now with continual learning and things like that, it seems that kind of it's a blur out there. So how, how should the platform look like?
This is the multi-$100 billion question, isn't it? I think because we run into two things. I mean, you heard about Maya.
Yes, of course.
And Maya is optimized for inference. Then you hear about NVIDIA's chips, which are optimized for the most part, their main line for training. And then you mentioned like gRPO or DRPO or any of these post-training things that are happening in the loop with with it, where you're doing inference at the same time you're doing the training. And so, whenever you've got a situation where you can optimize for efficiency, obviously that's going to be what you want to do, especially at the scales you're at, where you can save literally tens of millions, hundreds of millions of dollars by optimizing for some specific path. But when you optimize for that specific path and then things change, and they're not a good fit, that can be a big problem. And so it's this tension now, because we haven't even, like you said, the evolution of these architectures hasn't finished. And so if you over-optimize for one workload, you could run into trouble. So the question is how general should we be and leave money on the table in the short term, because in the long term, we're going to be protected against changes in the architecture or in the application requirements, versus taking advantage of optimization now and potentially being bitten by it later. I think that's the tension that you see.
Absolutely.
Yeah. All right, so we're down to a couple minutes left, according to the clock up here. So I want to thank you for coming and spending time with us at Build. Your impact on the industry is monumental, and it's gracious of you to come and take time out of your day to share your thoughts on the evolution of AI infrastructure.
Yeah, thank you. And we haven't touch on
confidential computing?
On confidential computing. So before going, I know that this is a topic dear to your heart, Mark. So can you say something about like security, governance, and so forth?
Well, absolutely. I mean, they're all from security and governance. We didn't really get time to deep dive on this, but when it comes to jailbreaks and prompt injections, I've been doing a lot of research on this. This is, like I mentioned earlier, a big topic of evolution where we haven't bottomed out yet. I view it as kind of the early days when people were downloading stuff from the internet and just your fingers were crossed. This is what happens now when you give agents access to your company's private data or your private data or your access tokens, is you're kind of crossing your fingers and hoping that things don't go off the rails and you end up with a problem. And we've seen some high-profile examples just in the last few months of people getting burned by prompt injections. So I don't think we've come to the reckoning yet on that and people understanding the risk. And then with confidential computing, that is another layer of, the clock just reset to 5 minutes. So we got another 5 minutes. Okay.
So now you can.
Okay, I can. Yeah. I think backstage they liked the answer so much they wanted me to continue. So I can talk a little bit about confidential computing now, which is it's independent of AI, of course, but related in some ways, because if you think about the sensitivity of the data that people are processing with agentic systems, if it's in a personal context, you're saying, hey, I really want you to help me with my medical advice. I want you to help me with my financials. You're giving these agents so much very personal and very sensitive data about yourself. And if you're in an enterprise context, the way you get the value out of these models is giving them access to the sensitive data of your enterprise. And especially when you're hosting this in a cloud platform or some hoster that's out of your control, or even in your own environment, you want to minimize the trusted computing base, the code that has access to that data, to the smallest amount possible, where you can have the highest assurance that it's going to behave properly and where bad actors can't get to it. And confidential computing is now we've got another. It reset again. I was wondering, I was like, wow, we burned through that time really fast. So now we have 13 minutes left. So let me just wrap this up, and I think there were some more topics that we can discuss, and maybe we can take some questions from the audience. But confidential computing, for those of you that aren't familiar with it, it's hardware-based protection of data while it's in use. So the hardware itself is encrypting memory and creating a privileged boundary around the data such that nothing else on the system can get access to what's inside of that enclave, they're called. And it comes with a cool property the hardware provides, which is an attestation, where it can measure what's inside the enclave, and then the application in that enclave can offer that attestation to another system that then can look at it and say, oh, your data, your compute inside of an enclave, I trust that enclave, I trust your configuration, I'm going to give you a secret, typically a key, which allows you to go and process that data in the clear. And it's protected against so many of the threats that not having this enclave protecting that boundary against. And when it comes to agents, having an attestation of what is the agent, what is his provenance, do I know that the data that I'm giving to the agent is protected with the highest assurances possible inside that enclave, you're going to see a trend with AI and confidential computing that I think is going to really drive forward confidential computing. Confidential GPUs from NVIDIA, for example, confidential GPUs from AMD and even Microsoft's Maya processors.
Yeah, that's fascinating.
Yeah. Okay, so since we have more time on the clock now, which is kind of nice, let me go back to some questions that we skipped earlier for you. Okay, so, and I guess this is something we really haven't talked about, is developer experience. We've been talking a lot about infrastructure, but you've got all this complexity. When it comes to developer experience, there's so many options out there. There's GitHub Copilot CLI, there's the SDK, there's OpenClaw, like what, and there's doing your own loop, calling an LLM directly. We saw Simon Willison doing this with his own application. He didn't use any harness. What's the best approach? When do you decide, when do you use one harness versus a custom orchestrator? How do you code this and how do you measure what's the best answer? And in fact, I wrestle with this too when I'm approaching questions.
And me as well. But, but let me just give, you know, so I think that, look, my TLDR is that now we have, again, very powerful coding agents and so forth. And many of you, I'm sure, how many of you used coding agents? Right? Everyone, right? I do think that actually the biggest challenge is that, and this is, it's about how do you know that the code which is generated is going to work correctly for some kind of definition of correctness, right? Is doing what you hope you want to do, right? I think that's the key, right? And the more code it generates, the harder it is to do that, right? Because, and I think this was, you know, this is also was true before, right? Everyone here probably developed a production system, right? Or has been involved in developing a production system. Where do you spend most of the time? You don't spend most of the time in prototyping or writing the code. You do spend the time in kind of even, say, in, you know, debugging, then maintaining the code. It's easily 10-to-1 effort. So in some sense, what these coding agents are doing are going to commoditize that kind of writing the code, but the bottleneck will be more and more in kind of verifying. And yes, you can use these agents to say, hey, you know, check that, is that correct? But it's very hard. You know, some agents are lazy. So without you understanding the code, at least at this point, today, I don't think, and continuously testing it and enhancing the test, I don't think you can trust that code that is doing what it's supposed to do. Because the kind of reward hacking is very different for what you can think about. Let me give you just one example. I have so many examples about that, but I'll give you the simplest one. You mentioned earlier about load balancing. So say you are going to say, okay, I want to develop a load balancer algorithms and, you know, using the agents. And we did that. We have that, you know, a few months ago using EPLB, right, expert parallel load balancers and so forth. And then what you want to do is the metrics. You want this, you know, the load you are going to handle. You know, you want to maximize that load. Mm-hmm. Now, one solution is simply, which we've seen that because that's a metric, the hill climb, the load, is just dropping requests. Right? Now, you wouldn't think that when you tell someone, you know, even when you raise a PRD about the load balancers, hey, you shouldn't drop the request. It's just kind of understandable, right? But these models, you know, they are going to do that because they are going to maximize the things you told them to maximize, right? In the simplest and the easiest way. So that's kind of why I'm saying it, right? And there are many things which you can pass all the unit tests and so forth, and then when you look deeper, there are things which are, in a way, overfit to your test you couldn't imagine, right? It's like that's kind of the things you still need to, I think, at this stage. I don't know what will happen in a few months, in 1 year, but right now you have to be able to specify. If you didn't specify something, you can almost guarantee that the systems will find something around it. And there are 3 places the specification comes from. So one is basically, actually there are only 2, and you know, like one is that the training data set. The training data set you kind of train, and some specification come from here. Like for instance, 1 year ago when we generate the code, you have a lot of vulnerabilities. Now you have fewer vulnerabilities when you generate a code with agentic. Right? And the other one is from the prompt. You have to specify what you should do or not. If it's not in the prompt or it's not in the training data set, you know, it's going to find a way around.
Yeah, it'll fill in the blanks.
Yeah. So that's kind of, I think, is the main bottleneck. And yeah.
All right, so now we really have 6 minutes, and I'll give you a question that I think is the question that I get a lot. And I've got my own opinion about this, but I'm curious about yours.
So you'll answer after I answer.
Yeah, I'll answer. And this is, I talk to people and I explain I've got so many war stories of AI going off the rails. I and me and Scott, we have got this podcast, and I talk about how I basically sculpt, which I always have, but even with AI, I'm watching what it's doing. I'm control seeing it. I'm telling it, that's not what I want you to do, and I see it, creating this test or going off in some direction, filling in the blanks with something that is ridiculous or that I don't want. And I tell people this, and I say, you just can't give it a prompt or a PRD and expect that you're going to get a system that works reliably and efficiently and does all the things that you imagine you want it to do. And even if you go and try to specify it, you cannot specify it deeply enough to guarantee that it's not going to do things that you don't want. A lot of what we do is based off of kind of environmental context and just kind of the taste that we've developed. And so I'm like, I just don't see a path to this world where you don't need engineers that understand what's going on and don't know how to guide the system when it goes off the rails. And then I get this pushback of, no, Mark, you're just, that's a bet that I would take with you every day because it's going to be solved. Maybe 2 years from now, maybe 5 years from now, maybe 10 years from now, the AI will be so good that you won't need that. Your example where you said the load balancer was dropping requests. What if you have an adversarial code reviewer go look at the system and say, you know what, you shouldn't be dropping requests. And it's, is this system well behaved? It'll say, no, it's not. And so you just address that. So where do you lie on this? Do you think that, would you be bold enough to say it's never going to be solved? Or do you think we'll get to the point where we'll have the ability to give a specification, it'll come out great. And you won't need humans.
I think that in theoretical, from the theoretical perspective, it's very hard for me to see how it's going to be ever solved. And fundamentally because we know from Gödel that no axiomatic system can be complete.
Yeah.
So in some sense, that's kind of tell you something. I think that when we look at other techniques to do it, like for instance, assume that you have a formal specification. You can write in Lean, on Coq, and so forth. So from that one, if I have the formal specification, then you can generate the code, and then you can generate the proof that the code satisfies the specification. So that kind of is good, and you can see that. The problem is that obviously then you need to write that specification, which is kind of not easy. And even that when you write the specification, it cannot, it's like if it's incomplete, right? You don't specify a property because, like in this case, I write a specification for load balancers, but I don't write, oh, you shouldn't drop the packets, right? So maybe if there is a conservation law there, you can argue that you should put it in. But there can be assumptions, right? Because any specification, anything, you have to have some assumptions, right, to make the proof. But you are not going to imagine all the assumptions, right?
I think, what is a full specification? Actually, programming languages.
Almost. Even that is not. Let me give you an example. Even that is not.
Yeah, that's true. But that's
right. Like I remember, we have this kind of, I'm not sure, this peer-to-peer court system and so forth. I was young faculty there, still implementing all of these things, and really, I thought it's bulletproof. And we were testing it on this. I don't remember how many remember about Planner Lab. 20 years ago, this Planner Lab, which is kind of an infrastructure, internet infrastructure, where each organization have these servers, and then you deploy at these servers applications, and then you communicate. And it breaks. And I don't know what it breaks. It has to work. And when we look about, like it was an assumption we missed, and the assumption we made implicitly is a kind of transient connectivity. If A communicates with B and B communicates with C, then A should communicate with C. And in the internet as a whole, right, because it's not behind NATs and so forth, this has to hold. And it should have held, except that is one university which misconfigured their servers so that blocks some communication, some traffic, right? So that's kind of, I always think about that.
Example.
I couldn't, it's like, we are correct about the assumptions. it should have hold, but it didn't because a mistake in the configuration in the platform. So that's kind of what I'm trying to say. It's extremely hard.
Yeah. So now we are really, I think, at time. I haven't seen the clock jump up again. But it's been a fun conversation, really fun conversation. And if you like this is an experiment. It's the first time we've done something like this. If you like this, let us know. So we'll try to do it again. If you found it boring, also let us know. And I think the people that thought it was boring are probably already left. So I think
we have a biased audience here.
But thanks very much for coming to Build, and I hope to see you tomorrow morning in my Azure Innovation Talk, where I'll talk a little bit about some of these things.
Thank you so much.